can I introduce our speaker then? All right, so good afternoon, everyone, and welcome to today's seminar. We're very happy to be joined by Professor Christine Peter. Just to give a brief introduction, Professor Christine Peter studied chemistry and mathematics at the University of Freiburg in Germany. In 2003, she obtained a PhD at ETH Zurich and subsequently worked at the National Institutes of Health and the Max Planck Institute for Polymer Research in Mainz, Germany, as a postdoctoral researcher and an Emmy Noether research group leader. Since 2013, she is full professor for theoretical chemistry at the University of Constance in Germany, and the research focus of her group lies in multiscale simulation models and scale bridging approaches and the development of analysis methods for simulation data. Areas of interest range from peptide folding and aggregation, protein-protein interactions, to biopolymer mineral interfaces. Professor Christine Peter, thank you very much for joining us today. We look forward to your presentation.
Thank you very much. Thank you for inviting me here and for making this virtual get-together possible. So let me skip right away and see if that works. So yes, so what I'm going to talk about today is what we as molecular simulators who are trying to do scale bridging, where we use machine learning. So let me introduce first what we are actually doing. So if you speak about simulating molecular systems, you first have to settle on the level of resolution with which you want to describe your molecules. And in my group, we are mostly working with so-called classical atomistic models and classical particle-based coarse-grained models. What does that mean? That a given molecule, so here a biopolymer, a peptide, for those who know what a peptide is, I don't know how many mathematicians we have here. Anyway, it's a polymer of atoms, which is here shown in its all atom resolution. So this is what we would, what in our way of phrasing it is an atomistic particle-based model. So no electronic degrees of freedom. Typically, our molecules are embedded in solvent, which we also simulate, but which we don't show when we display the molecule itself. That's of interest to us. The other level of resolution that we focus on quite a bit is so-called particle-based coarse-grained model, which means that we group together certain groups of atoms into coarser entities, and we call them coarse-grained particles or coarse-grained beads. So here, for example, you see these green balls representing certain groups of our biopolymer. And what we are concerned with is to connect such levels of resolution. So basically to design coarse-grained models so that they are derived from an atomistic level of resolution, or go back. So we have a coarse-grained simulation and try to go back to an atomistic representation, which we often need if we want to talk to experimentalists, because lots of experimental information naturally lives on an atomistic resolution level. So this is the scales we are typically involved in. Maybe something about the simulation methods we are employing. In my group, we are mostly doing classical molecular dynamics simulations, which means we propagate the dynamics of these systems, or we propagate these systems in time by numerically propagating Newton's equation of motion. This is what we mostly do. Well, now it works. And as already mentioned, today's talk is mostly focusing on the utilization of machine learning methods for these scale bridging purposes. So going from atomistic to coarse-grained and back with the help of machine learning methods. Sorry. It's always when Zoom pops up, then the clicking doesn't work. I apologize for that. And I will mostly focus on two papers, or on the contents of two papers. One that is where we use a neural network approach to make a coarse-grained model. And the other is where we use machine learning methods to go back from coarse-grained to atomistic and come up with an atomistic representation of a coarse-grained simulation, which we term backmapping-based sampling. And an important task in this procedure is also the comparison of the sampling of phase space in these two levels of resolution, which is also aided by machine learning. So when we speak about making coarse-grained models, in general, there is several approaches. One is a top-down approach, where you have experimental knowledge about your system, thermodynamic data, macroscopic data, whatever, and you feed that information into a coarse-grained model, and you try to come up with a coarse-grained model that represents this real experimental observables. This is something I'm not going to talk about today. I'm going to talk about so-called bottom-up coarse-graining methods, where we have some higher resolution model, for example, an atomistic description. It can be really fundamental, meaning ab initio, including electronic degrees of freedom, or in between a classical empirical atomistic simulation model like we are using in my group. And then we construct the coarse-grained model from the classical atomistic simulation level. And if this is your strategy to have a bottom-up approach, you have to come up with a target for your coarse-grained model. And to phrase it in colloquial terms, you could say you want the coarse-grained model to do what the atomistic simulation does. And how does this translate to something more quantitative? You want to sample configurations in phase space with the same probabilities as the atomistic model or the atomistic Hamiltonian. Before I move on, let me point out that this clear cut between top-down and bottom-up approaches nowadays is not so very frequently upheld anymore. There is lots of mixed approaches where people use some bottom-up information combined with some experimental observables, macroscopic information to tune the coarse-grained model. So mixed approaches are not uncommon, let's phrase it carefully. But this is not what I'm going to talk about today. So if we speak about bottom-up coarse-graining, I already mentioned that we try to reproduce the sampling of phase space by the atomistic model. So that means, what does that mean? Let's phrase it differently. First, let me coin a few bit of terminology. So when we speak about mapping, we have, for example, here this chain, and these small beads are supposed to be atoms. So this is now a very simplified way of representing atoms. But anyway, so let's assume that this is an atomistic chain, and we have n atoms. Then we coarse-grain them into capital N beads. Then our configuration in phase space on the atomistic level is a 3 small n-dimensional vector of coordinates. And our coarse-grained configuration is then a 3 capital n-dimensional vector representing the coarse-grained beads. And this is what we call mapping. So when I say that we want to make a coarse-grained model that reproduces what an atomistic model does, what we typically do is that we first, for example, run an atomistic molecular dynamics simulation with an atomistic simulation model. So that let's use the symbol V for the potential on the atomistic level, which is then in the atomistic space, so with the described by the vector small r. Then we map the probabilities of configurations in phase space atomistically to a coarse-grained configuration. So we determine a coarse-grained probability in coarse-grained space derived from the atomistic sampling. And this is basically the probability distribution that we want to reproduce with our coarse-grained model. And in principle, there is, of course, there is a rigorous way of deriving from this probability distribution a model, which we can get from Boltzmann inversion. So we use this P small at Boltzmann inverted, meaning that we take the negative logarithm times kt, but that doesn't matter. And that would be a potential of mean force that we can directly use as a coarse-grained potential. That would be rigorous. That would be a rigorously derived coarse-grained potential, which yields us exactly the same probability distribution as the atomistic sampling that we've based the model on. The problem is it's rigorous. In that sense, it's beautiful. It's unfeasible in most cases because already with a moderately sized system, R is very high dimensional, which means that when we try to determine this probability density, we die the curse of dimensionality. So it's really practically not feasible to determine such a multidimensional potential of mean force. And moreover, and that's maybe even worse, by itself, this is of limited practical use because this coarse-grained potential here is, strictly speaking, only valid for exactly that system which you've derived it for, which means that it is a system that you could simulate atomistically anyway, because this is how you determine the atomistic probability density, meaning that all in all, that sounds not so practical. And from that, derive all the coarse-graining methods that you have, or many bottom-up coarse-graining methods that you have maybe heard about, that you are maybe using yourself. Iterative Boltzmann inversion, force matching, etc. Those are all coarse-graining methods that approximate this multidimensional potential of mean force. And I'm not going to go into that at all today. Of course, now you could also use machine learning methods to approximate this multidimensional potential of mean force, but this is not what I'm going to talk about. What I'm going to talk about is that maybe this is not so unfeasible, and maybe you can make this of practical use even by directly Boltzmann inverting this high dimensional probability density. And for that, we use machine learning. So what I want to show you is that we can train a neural network to represent a coarse-grained Hamiltonian that corresponds to such a multidimensional potential of mean force. And for those that are more into neural network architecture or neural network approaches, let me already mention we are relying here on a so-called classification-based training and on a convolutional neural network architecture. A bit more details comes next. So the example that we did this for is the system which is also here that I used for illustrating what I mean when I talk about scale bridging. So we have polymers of amino acids, but those are homopolymers, so they are more or less like normal polymers, so it doesn't really matter that those are biomolecules. So of so-called glutamic acid and aspartic acid, which is only relevant to those of you who work with amino acids quite a bit. So the relevant bit is that here you have these, in this case, oligomer that have these side chains, and we use a rather strange way of coarse-graining it by focusing only on the positions of those ends of the side chains. So our coarse-grained representation is rather special. That has historic reason why we have been playing with this particular coarse-grained representation, but it's nice for illustrating purposes here. So we have a somewhat unusual mapping for our particle-based coarse-graining. This is a rather sparse coarse-grained representation, and for the polymer people, we have no backbone beads here. But the method that we employ here is not limited to this particular model. So we could also use a different coarse-grained representation, but this is what we decided to use here. So what's the general idea of a neural network representation of these peptide free energy landscapes? So the general idea is that we have some internal coordinates which describe the 3 n-dimensional conformation obtained from the atomistic sampling. So we basically describe the conformation of the molecule by, for example, all pairwise distances. Then we feed that information into a neural network, we create the neural network in such a way that it produces as an output of the neural network the probability of sampling a given configuration in this 3 n-dimensional phase space. And that means we basically encode in our neural network this 3 n-dimensional potential of mean force. By simply Boltzmann inverting this probability density, we then have the potential of mean force. So if this is the strategy we follow, we have 3 tasks of increasing complexity. First, we need to make such a neural network that returns the comparatively high dimensional potential of mean force for a given chain. But then, of course, we are not satisfied, because just returning the potential of mean force for a given chain doesn't give us anything that we couldn't have simulated earlier, already atomistically. So we want a neural network that can deal with several chain lengths, and as such, then the neural network to be able to predict how long chains behave. I apologize. So let's first start with the first task, creating a neural network that returns the high dimensional potential of mean force for a given chain. So how do we do that? We do that with so-called classification-based training. So we have a set of atomistic molecular dynamic simulation conformations, so conformations generated from atomistic simulations. Those we map to coarse-grained coordinates. So you find this here. This is our input data set for training. Then we generate a fake set of which we exactly know the probability density of sampling configurations, for example, to make it uniform or something. And then we train a neural network to recognize whether something is a real data point or a fake data point. And that means we minimize the cost function of distinguishing whether it has been a real data point or a fake data point. And one can show, and there I refer to this paper over here, which is actually not so new. One can show that this neural network outputs for us the probability density of our original data distribution. That means the output of our neural network is exactly the probability density that we were trying to determine and that we couldn't determine by simply binning probabilities because it's a too sparse space. And then what do we next? What do we do next? Once we have trained our neural network to return this probability density, we can feed this probability, these probabilities into a Monte Carlo algorithm as basically use this as a metropolis accept reject criterion. So we make Monte Carlo moves with the return of this neural network. And that means this Monte Carlo sampling that we then do generates an ensemble of structures with the desired Hamiltonian that corresponds to our R-dimensional potential of mean force, or N-dimensional, I should have said. Yes. So means that with this trick, we have made a Monte Carlo generator of structures in our coarse-grained space. So far, we have a neural network which returns the high dimensional PMF for a given chain, and we can use this in a Monte Carlo setting. Now we want a neural network that can deal with several chain lengths, not only with one chain length, and we want the neural network to be able to predict the behavior of long chains, meaning that we want to train on multiple chain lengths and then ideally use it on the chain lengths that we've trained it on and on new chain lengths, which are even longer. And for that, we use a convolutional neural network. So how do we do that? We use our polymer and chop it into tetrameric segments. And for those tetrameric segments, we use internal descriptors that basically describe the conformations, so the molecular structure within this tetramer segment, so which is the internal pairwise distances. We use also a few distances that denote basically excluded volume, and we use a triple product of several of the internal distance vectors to make sure that we have something like chirality correctly represented in the model. So those are our 16 descriptors that are used to describe a tetramer segment. And then we use a convolutional neural network of different filter sizes. So filter size of 1, where we input always the information of a tetramer segment, and a second level where we have a filter size of 3, where we use 3 adjacent tetramer segments as input. And by using such a convolutional neural network architecture, we basically can run through the entire chain, but the training doesn't depend on the lemma that we use for training, and thus it does also not depend if we then want to predict conformations on the chain lengths that we want to predict a conformation for. And if you want more details on that, we can maybe do that in the discussion. So let's now do something that's, now that we have a model, and we have a model that can produce configurations in coarse-grained space, let's validate this neural network coarse-grained model. Let's first look at properties that were not given as an input. So basically properties of the chain that we haven't used for training. And let's also look at molecules that were not used for training. Here is a first comparison. So what you can, for example, do is you can look at the end-to-end distances of polymers. And let's look at the end-to-end distances of hexamers, heptamers, octamers, and decamers of our polymer. And what you see here is the data that was used for training. So that's basically atomistic molecular dynamics simulations of hexamers, heptamers, and octamers. And of course, only the tetrameric segments were used. So the end-to-end distance by itself was not part of the training data set. And we can compare now these end-to-end distance distributions to what the neural network Monte Carlo simulation spits out. So you see that for the hexamer, it looks very close. For the heptamer and the octamer, the quality is, so to say, decreasing. And now we predict also decameric chain lengths that were not part of the training. We see that basically the covered range of the distribution function is good, but the fine structure is not reproduced anymore. Here you see also for comparison data from a very long MD simulation that was also not used for training, because we realized that especially for the decameric system, this was actually not fully converged simulation anyway. So take home from this is that the neural network model doesn't produce perfect perfect conformations of the chain, but it looks as if the overall range of end-to-end distance distribution, for example, is quite decent. We can also look at other descriptors, for example, internal distances that are a bit shorter. So for example, 1 to distances between hexameric segments. And there we can see that, for example, here for the heptamer, the neural network is actually pretty good at reproducing distinctions between, for example, the first hexameric segment versus the second hexameric segment in a heptamer. But this is now like fine details. So we can, what I would like you to take home from this is that with several of these collective variables that we've used for validating our model, we actually found that the neural network coarse-grained model does quite well. But this is one probably wants to have a different way of comparing the atomistic behavior of an atomistic simulation with the neural network model, not looking at distinct collective variables or so. And this we can do in the next step, and we can do it as a byproduct of producing atomistic structures that correspond to the coarse-grained data. So in the next step, what we do is basically now is we use the coarse-grained conformation that we got from the model, and we produce low-dimensional representation of the coarse-grained sampling and also of atomistic sampling, which means that we rely on dimensionality reduction methods to describe the sampling in configurational phase space. And we want to use those maps to backmap. So backmapping means that we generate atomistic structure for a given coarse-grained configuration. And as a last step, we want to use the coarse-graining to atomistic backmapping then to initiate new atomistic simulations, which means that we want to expand a possibly limited atomistic sampling. At the heart of this second half of the talk is that we need certain features, again, to describe our configurations. So we need internal collective variables that we use as an input, for example, for the dimensionality reduction. We need a dimensionality reduction method, and we need a method to compare how similar or how different probability distribution in these, for example, two-dimensional maps of configurational phase space are. So let's walk through the workflow in a sense. So we have the simulation data, typically in Cartesian coordinates, either from molecular dynamics simulation or from the Monte Carlo model. Then we generate an input data set for dimensionality reduction, where we again determine certain internal distances, or where we do sometimes in another setting we also use dihedrals, but here we use internal distances, so distances between the coarse-grained data point, coarse-grained coordinates. Then we use the dimensionality reduction methods. Many of you probably know principal component analysis or multidimensional scaling. From dimensionality reduction, we generate a map in a low dimensional space. Often it's two-dimensional if you want to use it for illustration. Sometimes it's 3 or 4 or something dimensional, so still low. And on that map, we can also then cluster and determine conformational states. So in the example I'm showing next, we use a dimensionality reduction method that is called SketchMap, which has been developed by Parinello and also Ceriotti when he was, Michele Ceriotti when he was in Michele Parinello's group. So it's a multidimensional scaling like algorithm, for those who know what multidimensional scaling is, but with a certain peculiarities that are tuned or that are designed to make it particularly useful for molecular conformations. Again, if you want to have more details, maybe we can discuss it later in the question session. And we have been using SketchMap to produce two-dimensional maps of our peptides for which we have atomistic data, so real atomistic simulation data, and for which we have neural network Monte Carlo data. The input features into the dimensionality reduction here are the pairwise distances between our functional groups. You remember the functional groups that were the endpoints of the monomers in our polymer. Those functional groups were the points that live in coarse-grained space, so the coarse-grained centers. So we make two-dimensional maps, for example, here of an oligomer of 7 aspartic acid. We make a two-dimensional map of a decamer of aspartic acid. We make of a heptamer of glutamic acid and a decamer of glutamic acid. And these are 5 microsecond atomistic simulations. At the time, that was pretty decent sampling. Here is the data coming from our neural network coarse-grained model. So using this Monte Carlo engine, producing structures with this neural network model. and again, mapping them to the same two-dimensional space. And by eye, it looks kind of okay here for the heptamer of aspartic acid. By eye, it also looks kind of okay here. Likewise here. If you look at the decamer of glutamic acid, you see that by eye, maybe the minima are at the right places, but there is definitely regions missing. And there is definitely, it's definitely not agreeing all over. So this is the molecule we're going to focus on now. So why do we see the deviation? There is two explanations possible. One is that this atomistic sampling here is simply incomplete. This is a molecule that undergoes quite a lot of conformational transitions. And in a 5 microsecond atomistic simulation, the atomistic simulation might simply not have seen the entire space available to that molecule, and it might even have missed relevant regions. Like, on the other hand, also the coarse-grained model may simply have errors. We actually know that it has errors because we have looked at the end-to-end distance distribution earlier on. So the idea of so-called backmapping based sampling is that we use the coarse-grained sampling here to initiate now lots of short atomistic simulations. We generate the starting points of these atomistic simulations from the coarse-grained map, meaning that they get reasonably good initial weights. We use the atomistic model to run then the simulations, but still it's a lot cheaper in effort compared to these 5 microsecond atomistic simulation. And we hope for the atomistic model to correct then for coarse-graining errors. So if we have started an atomistic simulation from a structure which is not quite spot on compared to where it should be on the atomistic, from the perspective of the atomistic model, you would expect it to move a bit on and to go to a more relevant region of phase space. And what we would like to do is we would like to quantify the quality of the sampling. And this is what we're doing next. So how does the backmapping based sampling work? We project our coarse-grained data, which we got in this case from our neural network model, to a two-dimensional map. We run a few atomistic simulation. So this here should be the initial coarse-grained map. We run a few short initial atomistic simulations, which are maybe here at these points. We project these into the map. Then we determine certain target structures from the coarse-grained map. That means we use the coarse-grained ensemble to say, oh, we want to have atomistic simulations at these points. Then we backmap, so meaning we create plausible atomistic structures that correspond to a certain coarse-grained point on the map. And then this we do by using this so-called distance restraints. This is more for the experts in simulation methods now. And then we run unrestrained molecular dynamics onwards from these points. And that we can do in cycles. So we run this maybe n times, whatever, until we are satisfied. And the question is, what does satisfied means? Let me first give you lots of maps. So here, these two you have seen already. This was the map generated from our neural network model. It's the one enveloped here in green. Here is the map that you've seen earlier on, which comes from a 5 microsecond atomistic simulation, which is definitely a lot sparser. Here you see a map of backmapped atomistic simulations, and the atomistic simulations initially were really very short. So there's only in a few points because they didn't have the time yet to deviate a lot from these starting points. And then we run these atomistic simulations for we run more and more of those and for an increasing length of time. And we end up after 800 nanoseconds of running, in total, 800 nanoseconds. We have 100 points, and each of those 100 points we run for 8 nanoseconds. We get this map over here. Now, the question is, by this looks actually quite decent. If you compare this map here to this map here, it looks reasonably similar. How do we quantify now those differences? We use so-called Earth mover's distance. So what is Earth mover's distance? It's a technique to compare the deviation between two probability densities by, in a sense, measuring how much Earth you have to shovel to convert one map into the other, in words. For the mathematicians, Earth mover's distance corresponds to the so-called Wasserstein metric. I don't actually know how to pronounce it, sorry. So what we do is now we determine the Earth mover's distance of this BMBS, so backmapping based sampling, as a function of length of the backmapping based sampling. The deviation of this with respect to the coarse-grained reference and with respect to the long atomistic reference. And what you see here is that the deviation from the atomistic reference decreases gradually. So this map here is this close to this map. At the same time, you see that you already start relatively close to the coarse-grained map, which is no wonder because we've taken the starting points from the probability derived from the coarse-grained map. But then the interesting bit is that you, with more sampling, get closer to the coarse-grained map, which is not surprising because we simply generate more data. But then when we increase the length of the sampling further, we go away from the coarse-grained. The Earth mover distances increase again. What does that mean? That we decrease because we have more data. Now it increases again because this growing atomistic sampling repairs for errors in the coarse-grained probability density. So meaning it repairs for deficiencies in the coarse-grained model. So an intermediate summary is that our neural network coarse-grained model represents the atomistic conformation surprisingly well. We knew that already from these end-to-end distance distributions, but these maps confirm that conclusion further. The Earth mover's distances are very useful to quantify the differences between these maps. With backmapping based sampling, we can very efficiently produce an atomistic ensemble based on a given coarse-grained sampling. I mean, you saw that this was 800 nanoseconds of atomistic simulations compared to 5 microseconds. The backmapping based sampling ensemble recovers the atomistic sampling, but seems to exceed its extent, meaning that we sample the map more extensively. And, the backmapping based sampling seems to repair for errors, deficiencies of the coarse-grained model. So now these two last points of conclusion are not fully confirmed yet. So the question is the backmapping based sampling really better than brute force atomistic molecular dynamics? And do those conclusions hold for other types of coarse-grained models? So let's first address the first question. Is the backmapping based sampling really better than brute force atomistic molecular dynamics? So what you see here is that we have evaluated the atomistic structures that we procured from long atomistic simulations on the right-hand side and from the backmapping based sampling with a different descriptor. This time we have been using internal dihedrals of the full atomistic structure, meaning that we had a finer picture of the atomistic structure as input into the dimensionality reduction. That's why the maps look different. So we really look into the molecular conformations on a backbone level. You see here that the BMBS, so the backmapping based sampling, seems to produce a broader map compared to the original brute force MD, but the relevant, of course, it's all atomistic simulations, the relevant, most important free energy minima, so maxima of the probability density, are the same here and here. Now, if we run some clustering method over those ensembles and look where the clusters end up, we, of course, find all the structures corresponding here to these free energy minima, but we also find that the backmapping-based sampling really finds relevant structures that were not part of our 5 microseconds standard atomistic MD, which means that the backmapping based sampling seems to find additional regions, possibly relevant regions of conformational phase space of the system. These are representative clusters which were missed by the free atomistic sampling. We can validate this further by improving the atomistic simulations, for example, with the replica exchange method, or for those of you who call this parallel tempering, so parallel tempering method. So we try to improve our atomistic reference by using replica exchange. And if we compare next to the backmapping based sampling, we really find that our 5 microsecond standard molecular dynamics had missed relevant regions of phase space, which were covered once we were doing this with replica, with enhanced sampling methods, meaning BMBS, cheap as it is, has found those regions much more efficiently. So BMBS, as we call it, finds meaningful additional regions of phase space. Let's make this a bit more challenging. We have redone this experiment, but this time not with our neural network coarse-grained model. If you remember, the neural network coarse-grained model was generated to produce the multidimensional potential of mean force, so to be as bottom-up as possible, so to be very good representation of the atomistic reference sampling. This time we did it differently. We used a coarse-grained model off the shelf that was constructed deliberately to be bad, to be disordered. And this is what you see next. So don't think that, for those who know the Martini model, Martini is a coarse-grained model that is an off-the-shelf coarse-grained force field that's easy to use. And normally that's pretty good for biomolecules. But we've tweaked it to be really bad for our polymers. And now we produce again a 2-dimensional map with different input features. That's why it looks different from all the maps you've seen so far. Now we project our atomistic 5 microsecond simulation into that very same map. And you see already by eye, this is where the dark spots are, where the relevant structures of the atomistic reference sampling are, and you see that they are basically completely missed by our bad coarse-grained model. Now, if we use this bad coarse-grained model to initiate a backmapping based sampling, we see that we recover, so that first we lose these regions of phase space, which are basically corresponding to a stretched but disordered elongated structure. So we lose the bad regions of phase space, and we gain structures in the relevant regions which correspond also to our true atomistic model, meaning that the backmapping based sampling even works if the coarse-grained basis that we relied on is bad. So the repairing for coarse-graining errors works even if our model is deliberately badly made. You can also again look at the Earth mover distances, but I will skip that bit now. I think my time is almost up, but we started a bit late. So let me quickly venture a bit into that part of the talk, but I will skip big parts of it. I would like to introduce to you a different system. So this is now a polymer of polymers. So it's a chain of proteins. So this protein here is called ubiquitin. We can make chains of ubiquitin, diubiquitin, and triubiquitin. And we can use input features into the dimensionality reduction, which describe the way how 2 of those protein blobs touch each other by using so-called residue-wise minimum distances. So we basically come up with a set of input features that capture how 2 of those neighboring proteins form an interface. That we can feed again into dimensionality reduction. So let me show you what a simulation like this looks like. So this here is now a simulation of an ubiquitin dimer. Of course, it is insolvent and it moves all over in space, but it has been projected such that we always see it fixed in space with one of the two units so that we can better follow what it does. And you see that the second unit is touching the first unit at different interfaces. Our feature set is designed to describe these interfaces, and this feature set has been then used to produce a two-dimensional map. And with the colored areas here, these are the relevant regions of a more global map, which are visited by this particular dimer. So we have been using this quite a while to characterize diubiquitins, so I'm not going to go into this, but since there is lots of ways how you can make diubiquitin, and you can make triubiquitin and tetraubiquitin, you easily run into enormous data sets. And this is the point I would like to make. Once we make these low dimensional maps, we need very, very efficient methods. And this is where, again, other machine learning methods come into play. So SketchMap, by virtue of being is of course also machine learning, but we need more efficient methods here. And for that, we have, again, used a neural network-based approach to tweak the dimensionality reduction, or to do that more efficiently. So we've been using, that's also not uncommon, as a basis, a so-called neural network autoencoder. And but we have modified it, and the method is called Encoder Map. So what is behind Encoder Map is that we generate an input data set, and then, as with the normal autoencoder, the target of the neural network training is that we have an input structure. It goes through the autoencoder through a low-dimensional bottleneck. So, for example, a two-dimensional bottleneck of two neurons. And then you have the decoder part, and the output is, again, a high-dimensional vector in your original dimensionality. And you compare basically the input to the output, and you train the network to have as good as the cost function is basically the difference between input and output. In that case, you encode as much information as possible about your conformation in this two-dimensional latent space of the bottleneck. That's standard autoencoder stuff, so probably lots of you know about this. What we have been doing is that we have added to that standard autoencoder cost function a second cost contribution, which is like with the SketchMap cost, tuned to be particularly relevant when you want to compare two conformations in some sort of conformational phase space. So we basically added a multidimensional scaling like cost. That's the trick behind Encoder Map. And it combines the advantages of a neural network autoencoder with multidimensional scaling, and especially the SketchMap variant of multidimensional scaling. And since my time is running up, I am not walking you through how useful this is, for example, to characterize triubiquitins, but I want to point out that we could run through the entire same thing, namely having a coarse-grained simulation of triubiquitin, have free atomistic simulations of triubiquitin, have backmapping-based sampling of triubiquitin, and by that, much improve the very limited range that's available to an atomistic simulation model, and use the coarse-grained model to produce a very reasonably well-converged atomistic ensemble. And with that, I close. So what I've been showing you is a neural network-based approach to make a coarse-grained model. I have been showing you the general idea behind backmapping-based sampling. I've tried to point out the relevance of using low-dimensional maps to compare the sampling into different levels of resolution, and I very superficially introduced Encoder Map as a very efficient way of doing that. It's a nonlinear dimensionality reduction method that's so efficient that we can process enormous data sets like we have them in protein simulations. And with that, I would like to thank my group. Here is the name of those people who have contributed to the projects I have been showing today. And of course, I would like to thank all the people that give us money for the projects and that give us computational resources. And I would like to thank you for your attention.
Thank you very much for your presentation, Professor Christine Peter. I imagine we'll probably have quite a lot of questions. So we have about half an hour available with Professor Peter. If I can ask people to raise your hands and we'll work through the questions in that way. We already have a question by Professor Alexandru. Please go ahead. Professor Alexandru, would you like to unmute and ask your question?
I was just clapping, I thought, but okay, since
I'll put you on the spot now, sorry.
Clap but
there was both.
maybe I did something wrong. Okay, so maybe since I have the floor, I'm not really an expert in this area of research, but if I understood correctly, I mean, unlike some things that we're doing in physics, where we need exact numbers, I mean, I have the feeling here, but correct me if I'm wrong, that you are not aiming for exact numbers. You're aiming for the qualitative description. Am I correct, or I'm
in a sense, yes. So when we deal with the molecules that I have been showing examples for here, those are comparatively big molecules that have lots and lots of conformations available. So the accuracy of the simulation is basically not an exact number. It's not even an exact trajectory in some sort of available phase space, because that doesn't exist, but it's statistical mechanics. So basically we have to make sure that our models produce the right statistical mechanical ensembles, meaning that then average properties that we derive from the simulation output, so from the simulation ensemble, they need to then be exact in the sense of corresponding, for example, to experimental data. Or in a bottom-up sense, they need to be exact if it were possible to simulate the very same system from scratch, meaning including all ab initio degrees, so all electronic degrees of freedom, which is not possible. So that reference doesn't exist.
Yeah.
Does it answer your question?
Yes, yes. It's very similar to what we are trying to do, but I'm just trying to understand why it works here and it doesn't work in other cases. What is really but okay, yeah. I let other people ask.
I'm not sure it works, just to follow up on that. So we strive for the correct ensemble, but it's very, very hard to validate. And this has not been part of my talk. So for the making, for example, atomistic force fields, you use then hard data for validation, and then only you get a glimpse into how good your model actually is. And here, when we compare two levels of resolution, we cannot even make them exact. So once you reduce the level of resolution, the model cannot be perfect in all aspects that you might ask of the model. So you always have, as we call it, representability problems. And definitely it's very hard to make the model transferable. So those are the so-called transferability problems. So if we have made a model to be good for a given subsystem or a given system composition, it's absolutely not granted. It doesn't even usually work to transfer it then to a different system composition or something.
Okay, okay. Thank you very much for this clarification. Thank you.
There's a question by Anastasia. Please go ahead.
Yes, thank you very much, first of all, for this enlightening talk. In fact, I have a couple of questions. It was very interesting in total. First of all, in your first part of the presentation, I saw the mapping scheme that you used on these peptides, and you used as coarse-grained beads the side groups of the dipeptides. And I understand this because in this kind of biological molecules, these are the most important part, let's say, of the molecule, and its functionality is based on the side group. But in a case of a polymer chain, can you say something about this type of mapping scheme, or in other words, if this mapping scheme affects the whole procedure?
I don't know how much it affects the whole procedure. I suppose that it does. This has been, I should admit that this whole neural network coarse-grained model thingy has been a project that we did for this particular mapping. We've always been thinking, okay, at some point we might try it on a different mapping. We are pretty confident that in principle it can work, but we haven't tried. And as you are saying, this is a very peculiar mapping in a sense. In a way, we wanted actually it to be peculiar because we wanted a mapping that doesn't work for a standard coarse-graining procedure. Normal coarse-graining procedures, very often your coarse-grained model very much follows the connectivity in the polymer. So you make the coarse-grained beads at positions where you know that there is real bonds, and then you can make a coarse-grained bond, which basically mimics the topology and the connectivity of your peptide. And here we deliberately went for a mapping where this probably doesn't work, because we have no bead in the backbone at all, where we know every conventional coarse-graining method will not work. But that was also because this was a bit of an exotic project in a sense. So I suppose it could also work if we went for backbone representations, but we haven't tried.
And just to follow this, because I probably didn't catch it very well, in the last part where you presented the proteins, which was the mapping scheme in that case? It was similar?
Oh, that was standard Martini. So I already showed when we were doing the backmapping. That was standard Martini. So
okay,
the protein.
Okay, because I lost.
Sorry. I made it too fast there. So that was standard Martini. And so that was only to show that this backmapping based sampling part also works for a big protein with standard Martini, but it was not using the neural network model to generate the coarse-grained ensemble. Yes. Sorry, I should have said this.
Oh, okay. Thank you very much. Thank you.
Professor Armandaris, please go ahead.
So, Christina, thank you very much. It was an excellent talk and an excellent presentation. So, naturally, I have a couple, let's say, of questions. So, first, just to understand, so the first case, do you have a single chain, let's say, model, a single peptide, or do you consider many peptides in this model?
It's one peptide.
It's one peptide only.
Yeah, it's
so,
one peptide only.
Did you consider, let's say, the situation to extend by incorporating, for example, intermolecular, let's say, features or descriptors?
We have. We have failed spectacularly. So that we have, if you recall, let me skip to that part of the presentation. Sorry, I need to go out of this mode because otherwise I will be clicking forever. You can still see it, right?
No, not actually.
It's not okay. Then let me share again. Give me a second. I skip to that part and I share again. Sorry. Microsoft PowerPoint share. Now you see it again, but probably in the not in the presentation mode. Yeah. You can see it? Okay.
Yeah, please.
Yeah, okay. So what we did is, because this is all segment based, we already had an excluded volume problem once we were making the chain longer. So we use then some pairwise distances that are truly non-bonded as part of our 16 descriptor set for this tetramer segment to make sure that we at least have a sort of self-avoiding walk in the behavior of that chain. But it's only sort of self-avoiding. So once your chain becomes very long, it's not even properly self-avoiding anymore. So we have no concept of excluded volume in here. So meaning that if now you want to decorate this with a multiple chain system, you would really have to think through that project anew and wondering how do you train it to know about excluded volume. Yeah. Which was not in. So yeah. I maybe to close this, maybe then it would be more feasible to really mix methods and to use methods like the ones that, for example, Markus Müller is using, where you really have a model that's taking care of the single chain behavior, and then you have. And then you couple it to a lattice or something. Yeah. The
slip link like methods. Yeah, more mesoscopic like. So this means that this distance to the two nearest other bits that you say is not enough in order to describe excluded volume effects.
Yeah, it only does excluded volume for a limited range of vision, but once it becomes a very, very long polymer, it's not excluded, volume exclusion is not granted any further. So the neural network doesn't know about it. So then you really have to do something more clever. And then the PhD student was finished with the project.
Yeah, that's always the case, yeah. So you should find a new brave PhD student.
Yeah, maybe.
And the follow-up on this, so if you have now, not let's say the homopolymer, but if you have a system with two different types, I know that you have also considered that, and I know that's not easy to do it, but I would like just to hear your...
In principle, the way we've pulled it together with this convolutional neural network architecture, it could work. You would have to have reference data of reasonably short combinatorial segments. So in principle, with a reasonable amount of effort, you could include other sequences, maybe not in sequences including the entire 20 amino acids, because that's a bit prohibitive, but it could work, but we haven't done it. Yeah. But with the architecture itself, it's not impossible. Yeah.
I'm just wondering, because as of course you also know, in all of these cases, all the different methods, let's say when you start having many different types of interactions, then you might have, let's say, serious convergence issues in all the algorithms. So
I agree.
Just wondering about that.
Yeah, I'm not even sure that this is particularly useful. So the whole idea here was mostly also proof of principle, and now one would have to consider what it is really useful for. I don't think that this is a useful approach for a protein. I think it is useful maybe for polymers, which homopolymers or polymers of limited variability. And then you don't die the death of combinatorics.
So in general of proteins, yeah, because of the many different amino acids, this could be you mean a bottleneck, actually. Yeah.
Plus then excluded volume would anyway be your major thing to solve. So I wouldn't touch proteins with this method. Yeah.
Okay, thanks, Christine. So let the rest of the people in the mic return my back.
There's a question by Yanis Tanis.
Hello, thanks for the nice presentation. I also have a couple of questions. You mentioned a bit about the transferability issues. I wonder if you have made any tests about the efficiency of your model under different conditions than those you applied at your atomistic simulations.
Yeah. Well, here for the neural network coarse-grained model, our transferability task was mostly to be able to make the chain longer. Beyond that, we haven't really done anything, which is not quite true. we have been playing a bit with the conformational changes that occur. These are side chains that you can protonate or deprotonate, that can be protonated or deprotonated. We've been playing with this a bit, but it has been nothing that we have been following up upon. Another thing in terms of transferability is that then we have been playing with the backmapping part. So once you decide that you use the coarse-grained landscape mostly as a starting guess to generate atomistic simulations, of course, you can then say, okay, we generate now atomistic simulations with a different state point, either a different temperature and you could now observe the shifts in populating that free energy landscape. But I know this is not the question you were asking. So for this particular project, we haven't been doing much about transferability questions.
Okay, thanks. And just another one. When you deliberately generated a bad coarse-grained model, you said that you lost the bad regions when you did the back mapping. I didn't quite follow how you did that.
So here you see, do you see the slide? I hope you see it. Here you see the landscape generated by the bad coarse-grained model, and you see free energy minima here and here. And for example, this region here, it corresponds to such structures. So they are rather elongated and they don't occur much in the atomistic simulation. Here you see the reference atomistic simulation and you see a blank region over here. And what we do is now we pick points from this map. We generate starting structures from these points. So we actually generate lots of starting structures from the dark blue and purplish regions. And we run atomistic simulations from those points. And we see that the atomistic ensemble rather quickly converges to the proper regions in phase space. And of course, we don't only pick points from those regions, but we pick points from all over, meaning that if you use the coarse-grained, and this was of course now a pretty bad example. So I mean, why would we choose a really deliberately bad coarse-grained model? This was more, the point was, if you have a coarse-grained model which has a sort of reasonable coverage of phase space, even if it is like the weights are off, that can still be a good basis to generate an atomistic ensemble. And you have, with the Earth mover distances, a way of monitoring it, because you can see how the Earth mover distances progress with increasing length of sampling.
So you still have a high probability to find the energy minima, the state that corresponds to.
So in the finally converged new backmapping based sampling, we find more or less the same free energy minima as with our original backmapping based sampling, which is in a sense the gold standard that we generated. So that was the best representation that we could get on the atomistic level.
Thank you very much.
Thank you.
Are there any other questions? I think at this point, people can just unmute their microphones and go ahead.
If there is not, maybe I can ask something more, Christine. I'm just wondering now a little bit from the technical point of view in the first part. Let's say when you check the convergence of the method, you train your network directly on the PDF, on the high-dimensional many-body potential of mean force. Did you try to do the training on the forces, on the derivative?
No, yeah, we did try. Actually, we did. So we tried also training on the forces, and this is a question I get reasonably often. But in fact, the forces are much more noisy. So to train them to do this classification-based training is actually pretty good if you really want the PMF to be very high. So it is capital N dimensional, or 3 capital N, if N is the number of coarse-grained beats. So this is reasonably high dimensional. So also the forces in this high dimensional space are pretty noisy. So we played a bit with it, and then we decided, no, we don't go for the forces, but we go for the probability density, and then we use Monte Carlo.
because we have seen exactly for a different system, but we have seen the same behavior. So we have seen very good convergence in the energy, but not at all at forces. And then, of course, when someone's trying to perform MD, you know, there are all these issues. Yeah.
What we have been, so the student has been playing a bit, so he was just playing on his own. What he did is that he was looking into those probability densities and looking into deriving forces in hindsight. So you could now, of course, use a Monte Carlo generator. So now you generate a Monte Carlo ensemble and then derive forces locally from this Monte Carlo ensemble and use that later again in an MD simulation. You could even do that. He played with it, but mostly to see what happens. And we came to the conclusion that it's not particularly useful.
What we've tried is to use an interpolation scheme in order to have, let's say, very smooth afterwards potential and then take the derivative. But again, the forces that you get finally, they are not the same as the atomistic scheme.
Yeah.
So you have some differences.
They are mean forces, and there is, of course, lots of ways to make good mean forces. So this was precisely what we weren't planning to go for. We probably would have fared better with force matching then.
Yeah, that's the other thing. So that's why you're using a Monte Carlo here. Huh?
Yeah. So we'd never have energies in the first place, right? Yeah. I mean, we only have probabilities in phase space, and those we implicitly invert, Boltzmann invert, by using these probabilities directly into the acceptance and rejection criterion of the Monte Carlo moves. So we never ever have energies in there. So
what are the Monte Carlo moves that you use again? Just
that was pretty standard stupid stuff, because we have no connectivity in the chain, so we basically make entirely random moves, and if they're stupid, we reject them. So we haven't been clever about the Monte Carlo. No. Okay. Maybe there one. I mean, if you really wanted to use that, but we are also not really experts in doing clever Monte Carlo.
Okay,
if you really wanted to do that.
If you don't need it, you don't.
I mean, I don't want to pretend that this is the neural network model here is of limited use. I mean, it is it's a possibility. It's a first step to show what's possible.
It could be important, yeah.
And yeah, practical use close to zero.
From my perspective, is you use let's say, especially in the neural nets, it's a more extended basis set in order to describe this kind of dimensional function.
Yeah.
So if you see it from the numerical, let's say, mathematical point of view, it's a very nice extension of that. Now, if it works practically, of course, it depends on the problem. And on the...
Yeah. And I think, I mean, this is also a bit of a time ago. Afterwards, many people that use these neural network based or other machine learning based ways that are more derived from quantum chemistry, they use these now also for these statistical mechanics simulations by doing the standard machine learning based sets, like what Cheriotti does or so. This is also being done. So maybe
I know there are a few works, but I mean, at least we have tried also using different things and different approaches. And, there are strong, let's say, serious problems with the convergence, especially of the derivatives.
Yeah,
so exactly. It's not really that you have something that it can work, especially if you have a high dimensional system.
Yeah.
And just as a final, let's say, question. So if you have a solvent, I think then it's straightforward to use it, your method, right? If you have a solvent.
To simulate a pure solvent, or
no,
polymer in a solvent?
Implicit solvent.
It's all implicit solvent here. So the atomistics is run in explicit solvent, but then the neural network.
For the explicit solvent, you just need to take into account again the excluded volume effect, let's say, with the solvent.
Yeah. So it's implicitly included. It's implicit solvent, and then when we backmap, we also reinsert solvent. So here I show the backmapping. The backmapping as if this was only the polymer, but the backmapping is a full solvated system.
Do you solvate it first? Or
we resolvate.
And then you resolvate again.
It's really quick. Yeah.
Yeah, that's fine. Yeah, for the water.
Yeah.
Okay, thanks.
Thanks a lot.
Alex. I think there are some questions more. Panagiotta, please.
Hello, thank you. It was a very stimulating presentation. I was wondering that this choice of the mapping, picking those particular groups. I think you mentioned that there are historical reasons behind it. I mean, are those groups the ones that are kind of active in the chemistry?
Yeah.
Or
exactly. So this is true. This is exactly the right guess. So this whole project was deriving from a different project. So it's a totally separate project, which is in the context of these peptides being modifiers in the nucleation or mineralization of calcium containing salts. So these groups here, they can be deprotonated. They interact with calcium ions in solution. And then these are modifiers to how calcium minerals form. And we had a project where we were interested in how these groups interact with calcium ions. And we wanted to have a model that pays attention to where these groups are. So this is purely historic regions. Of course, here in these simulations, there's no calcium, nothing. But that's why we were so interested in, most importantly, the positions of these groups. Yeah.
okay, thank you. Is that the figure? Well, since we're on this slide, this figure that we see on the bottom, is it? What exactly is this?
Yeah, okay. So on the left-hand side, we see a representation of the two-dimensional map coming from the coarse-grained simulation. So in fact, actually here it's a bit cheating. It's just a representation of the entire two-dimensional landscape. And then there is a zoom into the region of the landscape where the short initial atomistic simulation is projected that we needed to initiate the backmapping based sampling. So basically what we need for the backmapping based sampling is the coarse-grained map. And we need very, very short atomistic simulations to start this from. And then we, as a next step, we basically pick points from the coarse-grained map. And then we with position restraints, we pull these peptides into conformations corresponding to our coarse-grained reference data point. So this is what this here is illustrating. So this is basically illustrating where our atomistic simulations initially were placed. Otherwise, this is not particularly meaningful.
So this is a lower dimensional map.
It's a two-dimensional map.
So each of those points has many structures corresponding to it.
Yeah.
Is there a particular way that you choose one? Do you just choose randomly one of them for the atomistic?
Yeah. So we had a very, very short atomistic simulation, which we just initiated by setting up an atomistic system and run it for a few simulation integration steps. And the map was a two-dimensional map that was generated earlier on. It's basically these maps that you see here. Sorry, I apologize. It's not good. Let me move to. It's hidden. So maybe here you can see it. This coarse-grained, this two-dimensional coarse-grained map. It's a two-dimensional map into which all the data points from the coarse-grained ensemble are projected. And we try now to make an atomistic ensemble that reproduces the same two-dimensional map, so that has data points at exactly the same regions. And each region, there is many simulation data points. And the number of data points is encoded in the color of that map.
Okay. Thank you very much.
Are there any other questions?
I There are already many. And,
Yeah, I was going to say, I'm sure we've tied you up
we
for your
discussed
next
many hours.
meeting.
Yeah.
Yeah.
For the first time, I think it was enough.
I thank you very much. So this was very stimulating discussion, and I enjoyed your questions a lot. Thanks a lot.
Thank you very much for your time, for your presentation, for answering all our questions. And Vangeli, would you like to say anything else?
No, just to thank again, Christina, and I hope that we will have, let's say, the opportunity soon or sometime in the future to have Christina here with physical presence, finally.
That would be great.
And then you won't be able to escape all our questions.
Exactly, there will be much more time. Yeah, there will not be any excuse to escape.
But if there is more questions now, feel free to ask them.
Actually, we can. I mean, maybe we can contact you via email afterwards, or some of the students probably.
Of course.
All right. Thank you, everyone. Thanks
Thank you very much.
Thank you very much.
Thank you very much.
Bye.
Thank you very much.
Bye-bye.
Bye.